In this video, I'm going to go over some tricks to solve boiling point elevation and freezing point depression problems. In other words, some colligative property problems. First off, keep in mind that the equations for both types of colligative property problems are very similar. Delta T times the Kf for freezing point depression problems times molality for boiling point elevation problems, it's delta T equals Kb times the molality. Also keep in mind that molality is the moles of solute, and remember the solute is the stuff that you're dissolving, divided by kilograms of solvent, and the solvent is what you're dissolving it in. So if we put this information in these equations, what we really have is delta T equals the Kf or B times the moles of solute divided by the kilograms of solvent. So let's kind of stick with this equation, which incorporates the molality terms in there. The first thing that I want to talk to you guys about is the Kf versus the Kb. You're going to notice that all the Kf's are negative, and that's just to remind you that the freezing point depresses. So the freezing point goes down, whereas the boiling point goes up. So if you understand that fact, you can completely ditch this negative sign on the Kf. You don't really need it. And so remember, our equation was delta T equals the Kf or B all times the moles of solute divided by kilograms of solvent. In all boiling point elevation and freezing point depression problems, it's going to be useful to determine in your problem what is the solute and what is the solvent. Keep in mind that the solute is the thing that you're dissolving, and the solvent is the thing that you're dissolving it in. So breaking down this equation, really there are four variables. There's delta T, Kf, or Kb based on which type of problem you're doing, the moles of solute, and the kilograms of solvent. Something that's going to help you is to remember that as far as the moles of solute go, we can get from moles to grams and grams to moles using something called the molar mass. Keep in mind that if you want to get from moles to grams, we multiply by the molar mass. So if you're going, again, moles to grams, you multiply by the molar mass. Now if you're going from grams to moles, or this other way, you want to divide by the molar mass. The other thing to keep in mind is that 1 kilogram is equal to 1,000 grams. The first problem on your worksheet says how many grams of silver would have to be dissolved in 1,120 grams of ethanol to lower the freezing point by 0.25 degrees Celsius. Okay, now remember that we really have four variables, delta T, Kf, or Kb, moles of solute, and kilograms of solvent. Let's first determine what the solute is and the solvent. We know in this problem that silver must be the solute because it's the thing being dissolved, and ethanol must be the solvent because that's what we are dissolving in. So we know that the delta T is 0.25. This is a freezing point depression problem, so we need the Kf of the solvent, and remember the solvent is ethanol. Now if you look at that table up above, you see that the Kf is negative 1.99. Remember, we're going to ditch that negative sign because we already know that the Kf means that the freezing point is going to depress. And it's asking us for the grams of silver, which is a solute. So really we are looking for the moles, and then we'll figure out the grams. So that's our question mark. And then kilograms of solvent. We know that we have 1,120 grams of the solvent. So we need to change that into kilograms. Remember that there are 1,000 grams in 1 kilogram. So that's 1.120 kilograms of solvent. So this is 1.120 kilograms. Now let's plug in all of these things into our equation that we had before. So you might want to write these numbers down, and then I'll go ahead and on a different slide integrate these numbers in to the equation. So keep in mind that our equation was delta T equals Kf times moles of solute divided by kilogram solvent. So now let's insert all those numbers in that we know. We know that the delta T was 0.25, and we know the Kf was 1.99. Now the moles of solvent we didn't know. Let's just call that X for right now. The kilograms of solvent was 1.120, and let's solve for X. And once we know the moles, we can figure out the grams of silver. So that means that 0.25 is going to be equal to 1.776785,714x. You'll notice that I didn't round here. I don't want to round in the middle of the problem. So that's why I'm trying to keep all those numbers. Those are all the numbers that were in my calculator. So that means that x equals 0.25 divided by the 1.776785,714, which is 0.1407 with a bunch of other stuff after it. Now if we would have rounded here, we would have rounded to 2 sig figs. So I'm going to put a little line over the second number to remind myself that that's where I would have rounded had I rounded and stopped the problem at this point. But keep in mind that this is moles of silver, but the problem is actually asking us for the grams of silver. So like I showed you on the previous slide, in order to get from moles to grams, we need to multiply by the molar mass. So we're going to take this 0.1407035176 and multiply by the molar mass of silver, which we can find on the periodic table. That's 107.87. And when you do that, you figure out that the grams of silver is going to be 15.1776884. Since this is the end of the problem, we can go ahead and round now. This number would have been 2 sig figs had we rounded there, and this number is 5 sig figs, so we're going to use the least number of sig figs. So our final answer is only going to be 2 sig figs. So that's going to be 15 grams. So our final answer again is 15 grams, and I rounded that from 15.1776884 of silver. That's the final answer to this problem. The next problem I want to look at is the second problem on that same sheet. It says, what is the freezing point depression when 85.3 grams of oxygen gas is dissolved in 1,500 grams of water? Again, the first thing I want to do is decide what the solute is and what the solvent is. The solute is oxygen gas, because that's the stuff being dissolved. Keep in mind that oxygen gas is not just O, but it's O2. Remember that it's O2 because oxygen is a diatomic molecule. The solvent, the thing that we are dissolving in this problem, is water. Now let's take account all of the numbers that we actually have. So for the variable delta t, that's going to be our question mark. That's the thing that we're looking for this time. But the next thing was the kf or kb. We need the kf of water. And the kf of water is negative 1.86. Again, we're going to ditch that negative sign and just write 1.86. Now for the moles of solute, we have 85.3 grams, but that's not in moles, so we're going to have to change that into grams. Remember, the way we're going to do that is divide by the molar mass of oxygen, which is 32.00. So that means that we have 2.665625 moles of oxygen. And kind of like before, what I'm going to do is I'm going to write down, put a little line over where I would have rounded this number had I stopped this problem here. So we would have rounded this to 3 sig figs. So I'm going to put a little line over the third number to remind myself that that's where I would have rounded had I rounded at the middle of the problem. Okay, now kilograms of solvent is the next thing. And we don't have kilograms of the solvent, but we have 1,500 grams. In order to change that into kilograms, we need to divide by 1,000, because there are 1,000 grams in a kilogram. That's going to be 1.500 kilograms of solvent. So you can see, as like last time, I have 3 of the 4 variables, and I'm going to be looking for this fourth one using the equation. So let's go ahead and plug in what we know on the next. Alright, on this side I'm going to go ahead and plug into our equation, which is delta T equals the Kf times moles of solute divided by kilograms of solvent. So delta T is the thing we're looking for. Kf for this problem is 1.86. The moles of solute, remember, was 2.665625, and we put the line over the 6 to tell us that that's where we would have rounded had we rounded in the middle of the problem, divided by 1.50 kilograms. And so delta T then, once you do this in your calculator, is equal to 3.305375. Now we do need to go ahead and round. We're going to round to 3 sig figs. So our final answer then is 3.31 degrees Celsius. That's our final answer for this problem.